How do I run this thing from top right? Present? Okay. So this class started a few, this session started a few classes ago because we had a feeling that students were not, I mean, some of them, not all of them, needed some backgrounds about how to curve fit, what this RMSE means, all these kind of things. So I felt it was worthwhile to pass to you some wisdom that I got, and mostly from this book. This is my Bible since I started my master's. For numerical recipes, and the beauty of this is the text, not so there's a whole bunch of programs in almost any language. But the beauty is that it's written by four engineers, and they're very upfront and honest about how to apply things, what they're useful for. It's not your classic theoretical, very dry statistic book or curve fitting book. It's just a general advice on how to process data and look at things. So I'm really, can't say enough good words about it. But it came out just as I became a graduate student, so it was right on time. So what is statistics? A discipline concerned with the study of variability, uncertainty, and decision making in face of uncertainties. We're collecting, organizing, analyzing, interpreting data. There can be a whole bunch of different data that we're using. Some can be ordered like have values like your absorption values. Some are not, like taxa. So things are scaled. Things could be discretized, as they say, or like pain level. So why do we need them? They help answer questions. In our case, we might want to know. I might ask you because you need to know what bottle to take for tomorrow's cruise. How many liters should you take? You don't know, but you know that from when you did the lab, we collected a certain amount of chlorophyll. And so based on those, you can make inference and say, well, probably, a liter or two might be too much. I'm going to clog my filters. So maybe 200 ml. So you use past experience, past data to be able to make decisions now. You can ask questions like, how likely are we to find atoms in the water tomorrow when we go out? And you know that it's likely to be close to 1. The other use of it, which I like better, is that it really helps us reduce large data sets to its setting features. So yes, every paper I can add all the data I used in it to it, but nobody's going to look at it. But if I provide some descriptive of the data, like the mean or the median, how much it varied, that immediately help you relate to that data set. You don't have to see the whole data set for many questions. It's enough to get some basic statistics on this data, statistical description of the data. So it just helps us reduce giant data sets, especially today, into a few parameters that then we can relate to. So the use of statistics to make a point, statistics never proves anything. It says something about likelihood, but it does not prove anything. The other, which I learned early in my career, which I really, really like, is if you need very fancy statistics to make a point, your point is at best weak. So if it's not obvious, the thing in the data, you really have to dig very, very, very deep and find all kinds of these tests that we have to test and maybe this other thingy that you got from the web, and then probably your point is very. And you're not impressing your reviewer by using very fancy statistics. That's another thing. Don't feel like you need to go through many hoops. You just have to use it's a logical process. So we have a certain population that's out there, we sample, and we want to know something about how the samples represent what's in that population, for example, when we do with the IFCD. So we get taxon, we get pictures, but How close is it to what's out there? Things of that nature. We often use this, if you've all known it for many, many years. There's the mean, the variance, the standard deviation, the absolute deviation, the standard error of the mean. And what is the n that we put in there? What do you think? What? Number of what? So sample size, but does this number, so if I sample more, does the n goes up automatically? So let's think with the ACS. The ACS measures, 4 times a second as water flows away, or the baby center is once a second. What does this? So you're right. It's an independent observation by the instrument, but is the water the same, or is the water actually flowing through and change in that time? Is it an independent measure? So there is this concept of statistical independence of measurement. Just because I go to the dock and measure many times temperature at the dock, or I put a CTD in every second, am I learning much more about the temperature in this environment to the point in which the uncertainty goes really down, or because I'm measuring so frequently, the water doesn't have time to flow away, and I'm measuring the same water just again, and not getting really a realization of the environment that's in front of the slide. So n is really it's your independent, the number of independent measurements, and independent, can be done by different people, done different ways, there's many ways to think about it. Done in sufficient time interval that the measurement now is not fully correlated with the next measurement, that there's time for stuff to decorrelate and mix and move around. So depending on your question, this n can be very different. So if I measure for an hour, every second, my standard error of the mean is very small around my temperature at the dock. But if I'm coming tomorrow, the likelihood that the same temperature either is 0, given the time scale. Within that standard error that I think I have. So we have to use our brains and understand the processes that are causing variance to then decide, okay, if I really want to know what's the likely temperature here, how should I sample? How should I measure? What should I resolve? What are the processes involved? It's not just application of equations we see in books and then just go and do. Same goes with the phytoplankton community. I measure the phytoplankton community now, and measure 10,000s of diatom, but how fast would it change here? How representative is it of what's going to be there tomorrow, in an hour, in 2 hours? And that determines a lot how you're going to sample. Now, how many data are there between the mean and plus minus 1 standard deviation? 68%. Now, is this absolutely true? What did you assume when you said that? Exactly. So you assume already an underlying distribution. You have an idea what's the distribution of, say, diatom sizes here, whether it's small or not. You don't. So this number, if you don't know the underlying distribution, it's meaningless. It tells you something about variance, but it does not say that there's no 68% of the variability in between plus or minus. The other thing, which is these unknowns, is we have the feeling that if you have more measurements, we're decreasing our uncertainty. But if we're biased, we can measure until smoke comes out of your ears, but because you did not calibrate your instrument, you're off, and you might be completely off by a lot, but you don't know. So this is my fear. My biggest fear is this: is these biases that are out there because we don't understand fully our instruments, or don't understand fully how things relate to each other. That just because we measure a lot and we measure all over, doesn't mean we're reducing uncertainties. It could be you know, the chlorophyll B, what it does to the chlorophyll in a Turner barometer, to the chlorophyll A. And you think the chlorophyll A is perfect, and it just doesn't matter. You measure each carefully, filter very carefully, because you have this bias that you don't know it's 90 because you don't do chlorophyll. These kind of issues, these are the things I'm most afraid of. Because we put huge amount of energy to be extremely, extremely careful, but it might be that the technique itself is biased in a certain way. But sometimes we know, and sometimes we don't know. So we talked about if you are, as in this case, this is US Army males mean height data in inch, I think. These are all, yeah. Brings a distribution of, yeah, of height in inches. This is really well done with a normal distribution, or seem to be. But here are the percent of female dying every 5-year interval. Not look at all like a Gaussian distribution, and therefore, if we assume that the standard deviation tells us something, it probably doesn't. So another way to look at data is to ordinate it by just rank. Rank statistics is what we use for non-parametric statistics. So non-parametric statistics do not assume anything about it. And it's the advantage of this is that then you know exactly how to interpret. The median is in between 50% of the data and the other. It doesn't tell you how close it is to any one of them, but it's in the middle. Percentiles, similarly, you can do percentiles, you can do, so, you know, I like, so if you do the 68% of the standard deviation, the equivalent here would be like the difference between 84 percentile and a 16th percentile by heart. It would be exactly the standard deviation if you have a normal distribution, and it would be something else if it's not. It would be a measure of the deviation that one could use. You have the mode, which is the one that comes most often. Sometimes it's useful. What's very strong with this is that with non-parametric is that it's relatively insensitive to outliers. You can keep your outliers. You don't have to go and find them and throw them out from your statistics. They don't influence your median as much because one rare value does not change. It could, if you have a small number of data, influence about your mean or your standard deviation. So it's nice to use things that are robust. And so robustness means insensitive to small departure from the assumption. And this is a really nice example of how you can have, by eye, you see a very good line. But then there's all these other points that are going along. And if you use your classic least square canned line feed, these points are going to cause this line to mostly be biased relative to your true data. And there are methods that don't weigh these points as much, so they don't skew the line as much. You can still leave them in, but they will not skew your line as much. Even if you did a fit that instead of being a least square minimization, so when you use least square minimization, this point play much more role than any point that's near the line because it's the square of the distance that you're minimizing. And typically it's the square of the distance in one direction, in this direction. This is why this is taking the line so far ahead, even though there's so many points here. So if you even just weighted by the absolute difference, you're already reduced it by a lot. You can do the square root, you can come up with, there's many, many ways you can come to get a line that's taking into account more of the points than, that counts the weight of the points more the way you subjectively think they should be compared to these outliers. But we'll consider this outliers without having to throw them away. And you don't want, so the other thing is you don't want to throw away data, ever. The data is, from my perspective, is sacred. I mean, this is what you measure. This is a realization of the environment. It might be that there is a problem with your instrument. Unless you're sure about it, leave the data in. If you don't feel it should weigh as much in your feet, leave the data in, make it weigh less or not weigh at all. It's up to you, but leave the data in because it might be that there's something with these data that is really new science. They were measured in a different place. They were measured, there's something about them that then somebody else see in their data as well and suddenly discover why these are where they are. And there's a meaning to it. It's not just random. It's not, it might be the night data. It might be the NPQ data. It might be something that has a lot of information in it that you just threw away because you didn't know how to deal with it. So this is an example of, so you remember me diving with the IoT, with the sort of spectrum on my back case, now my back. What I did is basically dive a different depth above a coral reef. So this is closest to the coral reef. This is 1 meter above. This is 2 meters above. And then I went from coral reef to sand. So this is my eye, but this is the sand part. This is the coral reef part. And what you can see is that dependent on, you can see two things. One is at the top, you can see that the moment I go above sand, my variability goes down. And I'm measuring it with this distribution data. So the peaks are not in the same scale, so they're outside, but you can see a big difference between mean and median for in the probability histogram of the beam attenuation of particle Placido. There's much more variability above the coral reef than there is above sand. And that's due to most likely rare, and rare tend to be also large particles that were there above the coral. And the difference gets further and further. So this is, I think these ones are just above. This is the 3 different depths. I don't think they match the one. Yeah, they're different times. So this one I think is just above the coral reef. And what you see is the closer you get to the coral, the bigger the difference between mean and median. So coral, what they do is they filter particle out of the water and they form homogeneities close to them. So the further up you go from them, things are less variable than as you go down. And it might have some implication on metabolics. They take particles out, they filter out. There's a whole bunch of hydrodynamics around them that's different when you're close to them versus when you're higher up. And so these statistics can be used to say something about the distribution of particles around them. So statistics we use to say things about relationship between variable. For example, do we get blooms when nutrients are plentiful? Measure both. Or contrast condition. Is the diagonal kind of flash and domination associated with fresh water or other things? If you're near the coast, if you're in a place where there's a river coming in or not. These are questions you can ask, and statistics will help you with. A field of statistics that has not been used much in oceanography, and I've taken a class on Coursera in it, and I feel, and other people have started applying it to the field, is this Bayesian statistics. So Bayesian statistics looks at conditional probabilities. So if it's a warm day today, what's the likelihood that X will happen? If it's and that's based on a large pool of past data where we have much more information, not just about what we're measuring, but the general condition around us. What is the likelihood of species X blooming given a location, date, ocean color, and temperature? We haven't got there yet. Given a reflectance spectrum and RSST, what's the likely underlying nitrate concentration? Requires knowledge of this condition probability. And this is I don't know how many of you know this, just to show you an example that relates to it, that I absolutely love. How many of you know the Monty Hall problem? One. So it's a classic, beautiful problem. You have 3 nodes. Node 1, 2. you're a contestant in this quiz show, and you're asked to choose a door, any door. And what you know is that behind one of them there's a car that's going to be yours, and behind two of them there are goats. So you choose one of them, and you tell me which one you choose. And then I will what? Number two. And then I will tell you, and then I will tell you between 1 and 3 where the least goes. And the question to you: are you now going to change? You don't know what's behind it. Are you going to change to the other door or stay with the same one for the car? This should change. What? The probability should change. So let's say you chose 2. I tell you there's a goat here, and you'd say I'm going to switch to 1. Everybody says I'm going to switch to 1. As you know, switch to 1. How many don't think we switch? Most, it sounds like most of you say we switch. Another no. No. So maybe half and half. Okay, so let's just calculate the probabilities. So let's say you chose 2 and there's a car behind you. Okay, so that's scenario 1. The car is here. So there's a goat here and a goat. So you switch, you lost. That's 1. Probability, and the second one is goat is here. They told you there's a goat here, and therefore the car is here. And the last one is the other goat is there, and the same exact thing happens. So the probability is higher if you switch than if you don't. It's 2 to 1. Even though, and I was completely like Colin, I thought, what does it matter? You know, the probability a priori would be the same. And this is exactly what Bayesian statistics does. There is a change in the probability that occurs the moment you chose and they then told you where they were going. It's not any more the same as it was in the start, where there was 1 in 3 probabilities that the car could be anything. Yes.
Another way to think about this is when there's 3 doors there, you don't know anything about any of them. And you pick one, there's a 1/3 chance that you got the car. Now you've thrown out the 3rd one there that has to go. And now if you pick randomly, there's a 50% chance that you'll be correct. Rather than staying stuck with the original 1/3 chance of being correct. Very counterintuitive, and it's in every undergraduate probabilities. I remember just.
So this is an quiz show, and there's the savant was the woman who was running it. She at one time was the highest IQ in the US, and she kept getting letters from professors at the university saying, no, it's 50%, it's 50%. Go look at it in Wikipedia. It's really cool. And if you read this book, which I love, The Case of the Dog in the Nighttime, he has a whole section about it, just talking about and it is counterintuitive. I mean, maybe for some of you, it's obvious. Maybe and this is the power of condition. So again, this is where you bring extra knowledge. It's used a lot in meteorology. This is where you can also weigh the power of knowledge. If you know that Prochlorococcus does not exist in certain temperatures, you can use it in your inversion model, because now you have more information that's based on another parameter. But these are the kind of things where you conditional probabilities play a huge role. If you know that, given time of the year, certain seasons, certain things don't happen, then use them to predict a better version with your data, or better interpret what you're seeing. So it's really, really powerful. So relationship between two variables, often we do correlation coefficients. We can write them in small r, big R. We can do it for the rank statistics just as much as we can do it with the so for non-parametric as we do it for parametric. There's no problem doing it that way. And again, you don't have to assume anything. Now, a fun example that many of you might have seen before. These distributions all have the same mean, standard deviation, and correlation coefficient, and therefore R squared. What does it tell you? Yeah, so what it tells you is it's not enough, these are not enough, these parameters are not enough to describe data. To reduce this data so that you can trust that there's a good relationship between tomorrow. Just because somebody provided these, that's not sufficient. As a reviewer, you might say, can I see the data? And you put a figure in there so we can see the relationship. And again, and this in particular is driven by this one point. And this is this issue of R squared. Is the moment you have a large dynamic range, everything fits well. And fits well is fine. But the question is, how well can I predict this relationship from the data? And that's where one might ask. So, okay, now I give you, now you go and measure. How well can you tell me the value here from your measurement? So if you don't have, you might have an R squared that's very, very low. Let's say you only have these points. You can still predict, within this boundary, as long as you sample sufficiently, this parameter based on this parameter. Is it good enough or not? That depends. That totally depends on what it is you're after. If this is, and this could be within 50%, it could be within 1%, it could be within 300%. We don't have any, we do have rates here. So here it's within 25%. So it's parameter dependent. If I promise to grow to within 25%, I don't know about you, I'd be extremely happy. If I promise you temperature within 25%, you might not be happy at all. So it has to be related to the variability of your parameter in general, not necessarily in your sample, to help you figure it out. Now, we do love to see things like this, and this is why often when we have courses, we like to set a contrasting condition, because then the R squared are there. But it doesn't improve our ability to predict in any sense. And we have to be very cognizant of it. This is why I love this. I love this because it just shows you that R squared is far from being sufficient. Now, within a data set like your RMSE, they were very useful, this written square deviation, because they were all for the same data with the same range. But if you try to compare those to somebody else's, and they had a different range of data than yours, of course they're going to get a better feel of life. Because they have, they measured from, let's say they measured sea level from a river all the way to the open ocean. They have a full dynamic range. Well, if you're stuck here in front of the pier, all you're seeing is just the tidal, and there will be some variability, but you're never going to get the same much with it. But it doesn't mean that your measurements are as good a predictor as the one they do. They may be better. So be very cognizant of it. Yes.
I don't understand why using dynamic range is R squared.
Because you're adding, simply because of definition. Because you're looking at how far points are relative to them. Okay. The further you are, the better you go. As long as the noise does not increase also. So if you're very close to the mean value in your data set, you're not going to get a good R-squared. So regression models. So typically, in regression model, we think about a dependent and an independent variable. And the independent one, so the dependent is what you put on the y-axis, and the independent one is the one you put on the x. And your points, and your typical Excel regression will just work on passing a line that minimizes in only one direction, in this direction, the deviation. Because the assumption is that this independent variable has no uncertainties. Very good. It's your nanometers in the spectrophotometer that hopefully has been calculated. So this very often the assumption is that no evidence. So this is where model 2 comes to play, because let's assume, okay, let's think about something like I mentioned there. How about chlorophyll versus size? And chlorophyll, I have size. Do I have uncertainties in only one parameter? No. So I should not minimize only in one direction my lines. I have uncertainties. Any point has uncertainties in both directions. So I should take into account the fact that size is uncertainty. But if I put it into Excel, then it's something you can ask it. If I ask you to put it in error bars, you make some y. But when we twist a line, it's going to minimize the y. Because that's what's in there. And that's what's in most statistical package. So this is where, and I've seen you guys use it. And so this is where type 2 regression comes into play. In type 2 regression, type 1 regression, you only minimize in one direction, in the direction of the y particle, when you're trying to get A and B. So you have a cost function with all these fitting, line fitting, you have a cost function, it's defined, which is R squared. In this case, least squares, so it says a square value at the top, square. You don't have, again, you can fit without doing squares, before. But this is typically what you have in your package. And in an Excel package, what it will do is it will do this one with trying to minimize the deviation in the y direction. And actually, this is not good at all. You don't have the sigma to start with. Sigma I comes in if you want to weigh points by the uncertainty. You can do that as well. Put it into your theory. So this is one point more advanced than what Excel. Excel we do this. We minimize this. The difference between y and this model. Without doing an error, you minimize that distance between this and we'll give you the A and B. Any idea why these models were done? Why we started with these square models of that type?
Computational easy.
Not only computation, you can do that. You take the derivative, you take the derivative of this equal to 0, which will be a maxima or minima, and you can solve an annuity for A and B. And if you don't use square, you can't do that anymore. You use absolute value, because those are not differentiable. So the next step is you can take uncertainties into account. I have a point that has a big uncertainty, this one. And this one has a small uncertainty. And this one has a small uncertainty. Why should this one weigh as much on my line as the rest of them? Well, all you can do is just, I'm going to add an uncertainty into it. And then it's not going to weigh the noisy point as much as the less noisy point. Yes.
That is the uncertainty.
That's uncertainty the wider X more in this case. Yeah. Then you can also do it in both directions. You can do it in both directions, and this brings in these type 2 models. Yes. Automatically, when I have significant errors in both of my parameters.
But I'm thinking, for example, if you have a very effect, but you have some uncertainty, but the y uncertainty is way.
So then you might get exactly the same result if you do one thing. Yeah. No. But I mean, if I see your paper and you use type 1, And the two parameter probability measuring the scale, we often do probability plot because we learn so much more about that. Then the easy way to check is you're doing chlorophyll versus size, and then you do size versus chlorophyll. And you look at the line and you see by how different are they. If they're very different, one is that. If one has the reverse of the slope of the other, do that. Yeah.
Just a typo in the first slide. It should be 1 minus AX minus B.
The first guy.
Yeah. Just the X should be next to A, right?
You're right.
Okay.
So X should be next to the A number. Yeah, thank you. Same here as.
No, you got it right on there.
Thank you. And I don't know why, I mean, all the things are coming in the opposite direction. So actually, yeah, so this is actually, both of them are still type 1. It's just that they count errors. This is not type 2 yet. Type 2, you have to, in type 2, you have, it actually does, there's several type 2 methods, but some of them are just doing exactly that. The size of the chlorophyll versus size of the mean of the slopes of it's not just enough. And then, you know, with uncertainties, there's this beautiful package you guys got. This is the same package I used from Mari. There's a guy from Mari that I don't know why. This is this data, and everybody uses these codes. And they include if you have uncertainties and variable uncertainties. So this is go back to what Ben says. Often statistics are used in ways that are nefarious. So to sell us things that we shouldn't buy. We talked about all these things. So I'll move on. But this is a fun little book that my father had when I was young and I read. So smoothing of data, which is another thing we do. So how do we filter a noisy signal? And what is noise? And if you have questions, stop. So what is noise?
Instruments, electronics.
So instruments electronics gives us noise. What else do we refer to as noise? I mean, typically it's high frequency variability. You see there's some low, underlying low frequency changes, and then there's stuff on top. It could be electronic, it could be environmental. There's eddies, there's turbulence, stuff hysteria, and you get highs and lows coming in. It could be just rare large particles in our sample that because we sample a small volume, they're very rare. There's maybe 10 of them as a liter. So once in a while we get a spike in our instrument. But they're totally, they're real particles. So is it noise or outlier? It's on the highs or the low. So these are, and your relationship to it depends on what it does for you. If you don't have enough statistics to count them appropriately to be able to say something about the concentration or the properties, from your perspective, it's noise. If they were outlier, and you want to remove it. But if you have enough of them, you might be able to say something about the environment. So, and that's part of the problem we have is that they're rare. And often one person's noise is somebody else's signal. And I'll give you an example here. I use field as a way to smooth data, just so those of you who use MATLAB. So this is a method that Nathan Briggs has perfected, but goes back in history, back to Shifrin in Russia, and it's in his book, using fluctuation in the signals to tell you something about the size of particles. When you have very large particles, what you mostly see is their cross-section flying through your beam of beam attenuation or absorption or backscatter. And it turns out you can use, it's the variance to mean ratio. The variance to mean ratio, you have the sample volume there, you have the measurement time, which is alpha time, and you have this QC, which is this efficiency factor we don't need here. So you can use those to get at the average cross section of that rare big particle that causes the large spike. And from that, you can get information about their dynamic. So what Nathan did is, you remember these experiments we did in the sink with the aggregates where stuff fell down that may come from that? We had beam attenuation, we had backscattering, we had the least in there that tracks the size. So what he did is he basically took the same data and just looked at the fluctuations. And what he found is that you can, just from the fluctuation in backscattering or the beam attenuation of the least, to get a very good fit relative to the mean size of the least. So that the method was a good method. Just looking at his nose, the spikes gave him a really good estimate of the size based on the least. He also used this in earlier papers to look at size of aggregate falling down from blue in spite of backscattering with gliders in the ocean. So this is a classic example where you go into the noise to detect a signal you're interested to, which are the big large particle, the rare large particle in your sample. Yes, sir.
Does this relationship look as good on a long scale, or does it kind of fall apart?
It does not a lot of papers. So, I mean, obviously here it validates it, and this is particles that are too small for the least, and these are particles that are, I don't know why it gets the deviation. I'm sure it's discussed in the paper, but in the range where, in this range where this might be that there's too few of them in the time you measure. Yeah, it's discussed there. This method has a huge future. For example, we've never applied it to inline systems. And I think it could be very useful in inline systems to give you information about that, because we have all these measurements. We smooth it, we do mini binning, but this is what you get if you don't do it. You look at the difference. This is nothing though, because we talked about it a zillion times, but one day we're going to do it, but
it can also tell you.
But one of you might do it before us.
Right.
And it also can be, so that's another point, it also can be bubbles. I mean, there's a whole bunch of large particles in your sample. So you have to put some time in order to figure out what these really are. Another fun problem. So, and you've done them again. You feed spectra to optical data field all the time. So you have your CDOM spectra, and we've asked you in the lab to feed the model to it. So first, we measured it with 80 wavelength. Going back to what we talked about this morning, 80 wavelength with the ACS. How many parameters are we solving for? Good. An amplitude, which is this is going to be amplitude and slope. How well does it fit the data? Did it fit well, or did it on the lab? You get nice factor that this fit well. With various slope depending on range, but fitting well. So with two parameters, you're able to fit something that's 80 wavelengths. So do we have 80 independent pieces of information in those spectra? No. This is a classic example of it. Just because we have more wavelength doesn't mean we have more information. So how do we go about doing those kind of things? And same goes with the CP, although recently we found that there's a glitch that we can use to say chlorophyll configuration. A student from the class. So how do we fit those models? What do we do to fit them? So in this case, the assumption is that the error in the wavelength is relatively small, or for any purpose really small, given the range of wavelength we have. So we are minimizing distances in the y direction. And they could be squared. and they don't have to be squared. So we, again, define a cost function, effectively for straight and define a cost function depending on what we want. So this is our model. This is our data. And we're finding the values of S and AG that give us the smallest cost function. And it could be squared, it could be absolute value, and we can use the error in the measurements to weigh points where, for example, in the AC9 or the ACS, we know the blue wavelength has much noisier than the red ones, for example. So we're not going to weigh them. So when I got into the field, this was done in Excel. And because they were in Excel and because they did, and actually this is how Excel also does exponential models. The way Excel does exponential models is takes the log of the data and feed a straight line. What's the underlying assumption when you do something? Nobody knows that. What? No, it turns out the underlying assumption is that the relative error is constant for your points. So that sigma over the uncertainty over the measurements is constant. This is what, if this is the assumption, if you fit a line and you do a least squared fit to a line to get the parameter of an exponential function. Now, if your measurement value goes down, your uncertainty is going down. And what these people found is that the noise in the red was driving the crazy in their slopes when they did that. When they take the log of the data, feed in the line. So what they would do is to just have to remove this data. And just make it too much. And slow away. Without ever thinking what the fit line's doing. And the only reason it did it is because they used the wrong way of doing the fits. If you want to fit an exponential, why not simply do this? You know, it's a non-linear fit. It requires you to do, you know, to not use a package maybe, put in your uncertainties in each one of your wavelengths, but then you know exactly what goes in it. And the noisier wavelengths don't play as much into your slope, which they shouldn't, as much as those that are less noisy, etc. So if I pass one message to you is this: think before you apply and think what it means to apply a certain package or routine to fit your data. Okay. Any choice you make is pushing your data in a certain direction. So in this, you also have to provide an initial guess, but they converge well. It's not a big deal. So F-min search is the same function that you used with Collins' code. So a more robust varied function than a square one, for example, could be an absolute value one. There's nothing, you know, you're just not weighing outlier as much if you use an absolute value, and you can put that into, or you can even do a square root, and all that again is discussed in numerical recipes in that Bible over there. That's where I got it. So this is a text that Pete Humors wrote. So I'll read it and then I'm going to skip some of the stuff that's coming afterwards. But practicing science well requires comfort with error and good judgment of each practice. The judgment, which is not, it's something you have to think about. Otherwise, there's no way to tell whether observation for outside prediction from an uncertainty. Science makes the most progress when ideas that seem reasonable are discarded in favor of better ideas on basis of data. Measurement error is too large and sample size too small to distinguish which idea is right. Science cannot do that. This is where we rely on data. In science, error is a necessary fact of working with physical evidence rather than something to be avoided. It is uncertainty in measurements. Here we will assume that error and precision are identical. The only way to know about inaccuracy is to have some alternative method. Let's go back to disclosure idea. The only way we really know about the true uncertainty is to try to get to the same answer and completely independent. Not the same direction. Which means that even when we do ocean color, just because two ocean color sensor colors the same, they're still using a lot of exactly the same assumption in making the measurement of both of these. True independent would be something that uses a different way. The only way, which is not universally the case. Moreover, the two methods disagree is not always clear which is the more accurate. Now, so we recently compared, for example, Calliope, which is a LiDAR backscattering, with backscattering from MODIS. They disagree. 30%, 15% privacy. We don't know which one is what. One is inversion, like the GIP version, very similar to the Collins one. The other one is based on a LiDAR, which is measuring the signal coming back from the ocean. It's an atmospheric LiDAR, so it's over 20 meters. There's some parameter there that somebody is refusing to divulge how they got there. So they publish this data, we can get them, but we don't know how good they are. The two are different. So we at least know that we have this uncertainty to deal with. Then we have also arbiters. And everything is different by order. It's 20%. So it's really fun, but this is how we get to really move forward in science, because this tells us what are the true uncertainties. And these true uncertainties are not a measurement with the 20% is probably not how well we can predict PB from the 700 backscatter. It probably is at least 10%, but 20% seems large when you compare it to the other bubbles. Who knows? But this is where we move forward. And then we need to use known standards. So known standards are the beads, reflecting things we have, because those are extremely useful to constrain specific measurement that we can. So this is why we have NIST, the National Institute for Standards, and all over the world there's similar institute. They tell us that a centimeter is, a specific length. We need those because otherwise we swim in the sea of uncertainty. So I'm not going to go into this. If you've never seen how to propagate errors analytically, there's a great book by Taylor about error analysis and how to do that. It's too long, but I will talk a little bit about how you do it with Monte Carlo. So Bootstrap Techniques. So for example, let's say you wanted to know what's your uncertainty in this. In your spectral smoke after your feature light. It's not obvious. In absorption, in the base value, you might say, oh, I know something about how variable my absorption is in my measurement. It's probably some average uncertainties that the X is much harder. So how would I do it? So one way to do it is to, if you know the noise of your instruments, because you're measuring inside every wavelength, you can add for each wavelength here that you need to fix, you have a mean value or a median value plus your variability around it. So you can characterize that variability. The variability might be Gaussian, it has a certain width. It has some probability of being, if I measure over time AI with my sample that is not changing in my chamber, and I'm not burning my sample, so it's not drifting in time, I'm going to measure some variability around it. And I can then sample for my variability at each wavelength and then see what sigma I get. Now, this is not going to include uncertainty because when I do these measurements, I might calibrate better than or worse than Ben would for somebody else. So this is one kind of uncertainty, the one that was my variability while I measured. So I might want to add to it variability that has to do with the fact that Colin and I use different, she did on the spectrophotometer, I did in my ACS. There's a whole bunch of different things that will cause variability. But once I know it, once I have an uncertainty in my absorption, I can vary them and fit, and then see what I get. I'm going to get an S1. And I can vary them again and so on for my 9 wavelengths. And then doing it 10,000 times, I'm gonna get 10,000 different masses that will have a certain probability. This will give me my uncertainty. And uncertainty S. It's based on taking into account these uncertainties or everything else that I know about as a source of uncertainty in my prediction of A, and then the fixed interval. And often the assumption is that my wavelengths are independent. So once I choose an uncertainty for this guy, this one is not can be on the same side or below or whatever. And that might or not be true. So again, these are things to think about. You always want to put it in your brain. Are my assumptions correct or not? So these are called bootstrap techniques. They're very, they're not elegant, but it's just quick and dirty. I throw in my uncertainties, add them, subtract them to my measurement by sampling into a distribution, and then see how it influences what I'm trying to get. So you can do the same with Collins RRSs. You can add noise to the RRS and see how it affects the inferred parameters that you inverted to. You, in essence, when you did the fit for yesterday's lab, assumed that the RRSs don't have noise in them. And this will help you also know how well can I predict certain parameters from. So this is we've done it with, so you can use rand in Excel or rand n.m to get random numbers to help you sample from the.
So you're kind of just like, you're basically just adding noise to the, like, run this thing for
Exactly. 10 times the times, 20,000 satellite to then get your S parameter. Or in case of Collins inversion, you're running 10,000 times to see how the chlorophyll distribution changes for a given set of choices. Or, is it sensitive to it? Is it not? So yes, sometimes you can also do it analytically, but it's really quick and dirty way to get it. So this is just a recent paper came out of the NASA lab about incorporation of model and measurement uncertainties into a model. Yes. Sorry. It's, I mean, my understanding is all these statistical techniques in which you and this is what we call multi-color technique, where you basically using random number generators to help you choose values to which you're going to get it. So this is just one application. And again, it should be the same with hydrogen. I mean, you can vary within the noise the inputs to hydrogen and see how it affects the output, the RF. It's exactly another way of an application of that happening. So you're adding noise to see how or uncertainties to see how the uncertainties affect the output. So, and I strongly suggest you do it with hydrogen, because that again will give you a sense of when you see a difference between plugging in your absorption and backscattering and getting an effective structure, and you measure effective structure. Are they within each other uncertainties, or are they significantly different? How would you say? How would you tell? And that might be, also changing, doing many runs, including changing not just the uncertainty to your parameter to put it in, but also changing your assumptions. So, for which you don't necessarily know whether they're correct or incorrect. So that's part of the uncertainty project that you run through your.
So there's a difference, I mean, I think there's a difference between what I would call, maybe incorrectly, a sensitivity analysis, which is I'm going to put in, these 4 different spectra and see what the outcome is, versus putting in one spectra and adding random noise. And I think there's a difference. I think when you talk about bootstrap, I think you're talking about the random.
Yes.
Yeah, and when you're talking about sensitivity analysis, you're intentionally allowing it to vary 4 different ways, 5 different ways, And see how sensitive an outcome is to the variation in known inputs rather than random. They tell you different things, right?
Yeah, I guess I thought this graph was like subset your data into
Yeah.
5 different components. Run it on each different one. Random separate. I guess,
I mean, I have followed it bootstrap. I don't think it is. I think it actually is a sensitivity analysis, right? And I think I've used the term bootstrap incorrectly. So what you're describing is what I think probably is what we should call sensitivity analysis compared to randomly, using a random number generator to randomly add noise. But is your noise random? I mean, that's the other question.
Well, so you add it within its distribution.
Yeah.
So it doesn't have to be,
But you're assuming a distribution and you're randomly sampling the
Yes.
distribution, which is different than saying, I'm going to run this with 5 different,
completely different.
spectra going in or out or whatever. Yeah.
Completely different.
So I think it's just,
But they're complementary.
yes, they are.
Yeah, agreed.
They give you different, the interpretation is different.
So what they've done here is they came out with a way to get at backscattering, and that was not really the point of the paper. From blue, green, and red measurements, and they're getting backscattering in the green out of it. But what they really wanted, what the point of the paper is, how do we incorporate into a model uncertainties in both measurements and in the satellites and the inversions that go from it. So they go through a whole rigmarole, and I highly recommend that you look at it. It just came out. Now, information content. So this comes to the question of, for example, how many species can I get from remote sensing hyperspectral? How many pigments can I resolve from my ACS? Okay. And I mean, as we said, your RCS provide output 84 wavelength of absorption simulation. How independent are these measurements? And the measurements are done independently. You have this filter wheel going in front. It shines light through. It's done in a different time than another wavelength. So it's not, they are independent in that sense. But are they providing us information, added information, because we measure it so many ways? So we just looked at the result spectrum and we said, maybe 2, maybe 3 parameters of the result spectrum. So just adding wavelength is not going to add more information. But also relative to what? So this information content has to do relative to the accuracy of that method. And how do I look at that? For example, you did the fit of your CDOM spectrum, you remove it from your measured CDOM spectrum, and you look at what's left. If what's left, its magnitude is within the uncertainty of the measurement, you can't squeeze more information out of it. If it's larger, there's more information to squeeze out of it. So always, if you have, and Colin used to emphasize it, I think, more in the past, but you learn tons from looking at residuals between your signal and then what you fit to it, and then you look at the difference. And the difference, if it's significant, if you see specific peaks in specific places, then, oh, I used my wrong fire pack. I should use the fire pack that has a pigment in this region, because that's the region where my mismatch is large. So you looking at residual is extremely useful. Now, what about particular spectrum, and how would you go about doing it? So there's a whole theory in atmospheric science that it's one of its early practitioners wrote a book about it. It's forming in 1977. I forgot to bring the book with me, but it goes into looking at statistically at how much information can one get from a spectrum. And how it depends on the measurement uncertainty and uncertainty in the model, for example. So we did it with again, students from the class, and the project started in the class. Bibi Chow, Ali, a paper published in 2020, and there's different ways to do it. This is a slightly different way from Tony, but it's the same idea. And the idea here is I'm going to use many of you know about PCA, Principle of Point Analysis. So I'm going to look at signals. In this case, there's, I think, 300,000 minute being particular spectra from Tara going out to a variety of places. And I'll see how can I decompose that signal into its principal components. So if I do it with the raw spectrum, meaning I'm not normalizing anything, I'm getting these three that already determine 96% of the variance. What does the blue curve look like? Five absorption. Five absorption and hence something that co-varies with chlorophyll. And this really fast tells you that our particular absorption spectra in the open ocean are driven by algae. Nothing new there. But this is huge in terms of contribution. So then, and then what's left, looks like maybe some adjustment of pigments, some other things in there. But the next step we did is to remove from every spectrum a chlorophyll based AP. So a chlorophyll based AP was basically taking all these spectra first, those and many others, and seeing how they correlate with chlorophyll. And then remove in a nonlinear fashion, because we know that spectra do change with the magnitude of chlorophyll. And then remove that from our AP spectrum. Okay, so now we look for the residual after I remove what correlates with chlorophyll, nonlinear. So I have a nonlinear, I take AP in every wavelength, correlate it with chlorophyll based on the line height in every wavelength. And my model is nonlinear. So it's log, I'm looking at the relationship between log AP, log AP and chlorophyll. Because chlorophyll is log normally distributed in the ocean, among other things. And so I'm getting this model. This parameter has been published in 2013. And then we'll remove this model from the AP we measure, and then do this decomposition. What's left? After we remove the correlation chlorophyll. The order one thing, 91%, is that blue curve. What does this blue curve look to you like? There's no CDOM, it's H. Now, so this is already very reassuring. We see something that makes sense. And this is 90% of the leftover signal. And then we see in mode 2 and 3 things probably associated with pigments that are not resolved in this chlorophyll base. So we came out of this basically having the sense that in AP, from the data that we looked at, there's maybe 4 degrees of freedom above the root. If you decompose them in this fashion. 4 out of 88 were. That's not all. Yes, Mark.
And this is why, when Morel and Pierre in 1977 decomposed all of their radiance reflectance spectra, they could explain 90% of the variability with 3 components. And it's this, it's the phytoplankton absorption, it's the nap absorption. Add C on it, reflectance. But that's why also the data that I showed you from my inversion was the same. Like, you can explain most of the variability with really, really simple eigenvectors, and that eigenvector looks just like mine. And I measured mine like a different way 100 years before you did on a very small data set. They're really the same. They're so similar. It's crazy.
And your species information beyond what co-varies with chlorophyll. So again, I'll go back and say, as chlorophyll changes magnitude, it more likely also co-varies with change in species composition. But what is not covariant with chlorophyll in species composition is what you have in these curves that explain 6% of the variance. And this is what we hope to get from things. So we have to be very, very careful with the hope that there'll be enough signal to noise that we can do that. Yes.
So can you repeat the last part of those?
So The big, if you go to the website of PACE, the big promise is to be able to get functional times or other full functional group of final times. Beyond what we can already do. I mean, what we can already do is whatever covariates with chlorophyll. That we can do. The question is, can we do better? So already things change with chlorophyll. You know, when it's high chlorophyll, we know that it tends to be more diatoms. When it's very low chlorophyll, we know it's cyanobacteria dominate. Phocococcus, Staphylococcus dominate the diatoms. So that's already in the signal that we're measuring, that we can infer from chlorophyll. The question is, can we infer deviation from that kind of ecological state of, state?
So even though we can describe our severity already, the question is now who teaches us?
Can we do more than that?
Okay.
That's really the hope. That's the Mao paper in 2017. Can we get more? How do we do that? Now, there will be two polar limiter updates. So that will give us independent information to what we have. There will also be, we also, with remote sensing patterns, can do backscatter. There's no information on backscatter here. So that's more information. The spectrum of backscatter and information that is independent of this. So there likely are more degrees of freedom in the RRS that we can obtain. After when we have the atmospheric freedom and all that. But it's probably not the 3 ambient, there should be, it's every 3 nanometers. So the 60 wavelength we're going to get are not going to give us information on even 50. We get 3 or 4 groups, we have that.
But the big promise is we'll be able to completely modify the Beck-Clinton composition of the communities for each pixel. And that's the big promise. That's why everybody's working on a functional group model. Can you do better than just the relationship to chlorophyll?
That's really the metric. That's
If you
for
can't do
me.
better than that model for chlorophyll, then you're wasting your time exploiting something else.
So that for me, the metric is, can we do better than chlorophyll? Because chlorophyll we can do since zeros. Can we do that? And that's the metric in which anytime we come up with a new exciting version, try and do that. Show that in a place where chlorophyll predicted X, you got Y. That's the test. Yes.
So,
And what you do. Just want to know how to spell that.
Out. Yeah, it's the advisor, the ladies who did it. In front, I think it's in Frontiers. It's in Frontiers.
Yes.
So, again, if we think about it, we say, but why do we limit ourselves only to optical data? Why not add surface temperature to our inversion, distance from shore? There might be a whole lot of other parameters that could add information to our inversion. So if you think about it in terms of information, then you can think, oh, does water depth matter? How goes out to shore? Day of the year. All these parameters I think we don't use currently, and they might or not be relevant. But you have to use statistical technique to see whether they add to your ability. Once you have sufficient data set with species like them, IFCB, etc. So we also, we cannot blame the past or the future or whatever. When you don't have measurements of microscopy measurements, your uncertainty in food there is very large. Even though we have pigments from many places, they're not that many. They're not very specific in terms of telling us. So we're the science is, we're all the time kind of catching up. So there's more channels, but there's not enough data for validation. And we have more data for validation, but there's not more information for space. So we're playing this game. So to summary, statistics is something used logically. Just think about it. Don't just cite a paper on statistics and say, okay, I use this test because they used it. Think about, does it make sense for you? It does not prove anything, but can give you a sense of likelihood of testing a hypothesis. I strongly encourage you to study about information content, hypothesis test, and Bayesian method. And B, where they're often misused. In the last few years, there've been a whole slew of papers about what p-values really mean or don't mean. So if you use them, think about, don't use them again for the reviewers. Never do a test because you think it's going to impress the reviewer. Do it because it means something for you that makes sense.
That's where we don't ask for.
Yeah. But also, but feel free if the reviewer asks for a specific test to say, this, I mean, this is not relevant to my case, and here is why. Don't automatically do whatever reviewer asks you just to publish paper. It's a conversation you have. We'll talk about it next week. But I see your reviewer as your best friend. He's the last person to see your paper before you press on. So they're helping you to get the best product you can out there. And so the discussion you have with them, it's not a war. It's a discussion among scientists on what's the right way to present the data, what's the right way to, whether or not you can make the point you're trying to make. So treat it as such, and then you can use it as a conversation, not automatically do, oh, they actually need to do this, just to get it out. Questions? Yes, Kurt.
So here's a question. We all grew up doing these squares next to our data. Like that's supposed to do. Why do we do these squares? Why don't we do these values, these square roots?
Slide rules.
Yeah, it goes back to 100 years ago when people like Fisher were developing statistics. It was easy to take the derivative of the square. Derivative of x squared is just 2x. Anybody know what the derivative of the absolute value of x is? Remember from calculus? It's actually x over the absolute value of x. And it just wasn't convenient to play with. But you can do this derivative of a squared thing and get some nice clean math that you can play with on pencil and paper and prove all kinds of theorems and blah, blah, blah. And the reason you need to take a derivative, if you want to find the minimum of a function, you take the derivative and set the derivative equal to 0. So it was easy to take this derivative, set it equal to 0, and work it all out with pencil. And if they had these computers 100 years ago, we probably would have grown up doing minimizing the absolute value or something like that, which often makes a lot more sense than minimizing the square distance. That's all it amounts to. So there's kind of no reason now to stay in the B squares world if you look at your data and think, well, I've got this outlier, I ought to do things differently so that the outlier does and does not matter as much as the other points and so on. And of course, you almost have to write a computer program to do that because every CAN package like that I have to set up to do least squares fits. But it's just purely one of these historical flukes that's still haunting us today.
Right. MATLAB has a robust, not that I'm trying to say MATLAB, I mean, I'm sure it's true for Python as well. They do have robust statistics packages that allow you to do robust things. Look at them again, don't apply them blindly, and always look at what comes out and compare it to what you put in. So it makes sense. Just automatically run away with it. All good. Meg?
Yes.
So when you want to? Yeah. Sorry.
Let's start it up. Okay.